sounds hungry. Okay, welcome everyone. Let's start.
As opposed to sweet, but white.
Welcome guests. Welcome to Potluck Academy. And before we start, and before I know, Alex is an instructor in physics in BCIT, and he spent 2 years in CERN. And he's a certified guide in CERN, which means he knows pretty much everything about antimatter and the hadron collider and why we don't annihilate right away. So please welcome Alex Khramov.
Yeah, one more thing. Interruptions are welcome. This is an opposite of a lecture.
Yes.
You are supposed to interrupt.
Drinking is welcome.
You're supposed to drink, you're supposed to interrupt. You're not
can
supposed
ask as
to
many
just
questions
be
as you
polite.
want.
For some reason, the audio, if you plug it in, doesn't quite work, but it's all right. I'm gonna start out with
I was singing this in my head.
the
so
musical
thank you.
interlude. Got you all sort of feeling a little bit. Get me feeling a little bit ready. Anyway, the song that you're hearing is called "Nothing Else Matters." And it's a song by Metallica, and it's the source of the name of this lecture. We're going to switch it up a little bit and talk about, rather than matter, talk about antimatter. And we're going to ask, what is antimatter? Where is it found in the world? And why should we care? And I want to say that I personally find antimatter quite interesting, but it's not just me who finds it interesting. In fact, here we've got some members of Metallica. There's Lars Ulrich and Kirk Hammett in our laboratory at CERN. They came to visit us, and they actually signed our door, and this is where I stole the name of this talk from. The Russian version of the name of this talk was dialectический антиматериализм. Unfortunately, we couldn't get Marx or Engels or anyone else to come to visit our lab, so it had to be abandoned. I'm going to start with a quick glossary since this is going to be a talk in English, but I'm expecting questions in Russian, and I think if questions are asked in Russian, we'll see what happens with the language of the answers. Antimatter, антивещество, antiproton and positron have the same name in English as in Russian, as does annihilation, аннигиляция, and the opposite process that we'll talk about called pair production, рождение пар, a trap, pretty simple, and well, basically everything here should follow along. And with that, I want to start with talking about the world of matter that we know before we get into talking about antimatter. So I've put up here on the slides some objects made of matter. Here's a lat table from IKEA. Here's a sandwich, a ham sandwich, and we know that all of these things are made of molecules, which themselves are made of atoms, which themselves are formed of protons, neutrons, and electrons. And in the simplest situation that we can think of, here is matter. Here is the simplest matter atom, the hydrogen atom that just has just one proton, which has got a positive charge in the middle, in the nucleus, and around it we've got an electron orbiting. Of course, it's not orbiting in a circle, but that's the general picture. And then the proton, we know, is made up of sub particles called quarks. The proton of up and down quarks. So the question is, what would this picture look like with antimatter. And here I present to you the world of antimatter.
So quick clarification. What's
Yeah.
the third one? Up, down, and
Up, and down. So,
oh, two up
so
and
there's 3 quarks in a proton, but 2 of them are up and 1's down.
Oh.
Oh shit. Женя, вы вырежете потом. The world of antimatter with an anti-lag table from IKEA and an anti-ham sandwich. And can I ask the audience, what is the difference between this picture and the previous picture?
Shows the previous one.
Here's the previous one,
Okay.
and here's this one.
Nothing.
There's no, one says matter and one says antimatter. That's exactly right. There is no other difference. And in fact, a world that was made entirely of antimatter, for our purposes, would look exactly the same. So then the question becomes, why is it that we have these 2 things, both matter and antimatter? Why don't we just, call it all one thing? And to help answer that question, I'm going to ask you a question myself, which I hope you don't get insulted by, which is an equation, one of 2 equations to feature in this, in this talk. 6, you're out. No interrupting.
It's plus or minus
2 and minus 2 are the solutions to this equation, and it turns out that the difference between matter and antimatter is also a positive and a negative solution to an equation. Here is the world of antimatter. If you zoom in to the atom and look inside it, you will see that instead of positively charged protons and negatively charged electrons, you have negatively charged antiprotons and positively charged anti-electrons, which are called positrons. And I want to point out that the negative and positive charge doesn't really mean anything by itself. It's a convention, right? We say the only thing that positive and negative means is that negative things repel negative things and attract positive things, and positive things repel positive things and attract negative things. So if you had this anti-atom, it would behave exactly the same way as an atom, and your anti-ham sandwich would behave exactly the same way as a ham sandwich. It's just the behavior of antimatter and matter put together that is going to be different from matter acting with itself. Question.
Jumping ahead, but you're supposed to interrupt.
Yeah.
So if they're like the same, then
Yeah.
the world is full of one of them and the other is
Yeah,
non-existent.
so this is the most, the question that we'll get to that we don't have an answer to, right? Why is it, if they are the same, why is it that we are made of one of them and not the other one? To get to there, we have to figure out why is it that we should expect, just because they're the same, to have the same amount of them. And I'll talk about that later. I want to start with a brief historical overview, saying, okay, why is it that we know that this stuff exists? And in fact, antimatter was proposed basically immediately after the electron was discovered in 1898 by this Englishman named Sir Arthur Schuster. He is a spectroscopist, but he's mostly well known for his memoirs, and a story that he tells is that he was visiting a fellow spectroscopist's laboratory, and he overheard him talking to a student and saying, well, I will ask you to measure this value, and keep in mind that the closer your answer is to 3, the higher my opinion will be of you as a scientist. So in that time, you could sort of just go and get the answer that you wanted. And that is kind of how Sir Arthur went about it. He said he wrote a letter to Nature immediately after the discovery of the electron, and that said, wouldn't it be cool if he used, the language of 1898, but something similar to, wouldn't it be cool if there was same thing as an electron but with a positive charge, and that was enough to get him published in Nature. Standards have changed, I guess, since then. But during that time, it was a very interesting time in physics, as you probably know. It was sort of two revolutions in physics happening at the same time. One, people were looking at things happening at very small scales, where the Newton's mechanics that we know from school no longer applied, and you had to come up with a new theory, and this was a theory of quantum mechanics, which was developed at the beginning of the 20th century. At the same time, people were looking at things that were moving very quickly, close to the speed of light, and for that, again, the mechanics that were developed from Newton's time were not as useful, and so you had to have a new set of ways to solve problems, and that is called relativity. So you had quantum mechanics and relativity that were both being invented, and then you had to have some way to put them together, because inside the atom that we saw a couple of slides back, there was an electron, and an electron is both a thing that is very small and a thing that is moving very, very fast. So you had to have something that puts together quantum mechanics and relativity, and the first sort of set of rules that were developed for that were made in 1926 by Klein, Gordon, Fock, and a bunch of other people. And then shortly afterwards, it was seen that these would not quite explain the electron. I'm not going to get into why. And so it was sort of left as an open problem until 1928, where this guy who's somewhat cut off here, named Paul Dirac, came up with a relativistic quantum mechanical equation that explained the behavior of an electron. Now, Paul Dirac sort of had a different working method than most physicists of his time and of all times, which is that he sort of drew and wrote things that looked cool and interesting mathematically, and then only later checked to see whether they had some kind of physical application. And that is what he did here with this equation, which later came to be known as the Dirac equation. And he found that, similar to our x squared equals 4 equation, there were actually two solutions, a positive one and a negative one. And the negative energy solution not really making any sense, he said, okay, it would make sense for the solution if there was something like an electron, but with a positive charge. And being a person who writes down equations and then only then decides what to do with them, he said, okay, that means there must be a thing that's like an electron, but positive. But the problem was that nobody had seen such a thing. And the question then became, okay, Dirac, if you're so smart, and Dirac was well known for not only for his immense intelligence, but for his immense hubris. There's a thing about him that's a colleague said about him that there is no God and Dirac is his prophet. So he had a reputation. So of course people were saying, Dirac, if this is how it is, where are all these positive electrons? Why are we not seeing any of them? Right? And it turns out that the answer lies in the second equation that I'm going to put on, one that you also already know, which says that there's a way to there's an equivalence between mass and energy. And so given the correct symmetry rules, making sure that transitions are allowed, you can go between mass and energy, and a particular reaction can take an electron and a positron, two things that have mass, and convert them into just a bunch of energy. In this case, 2 or 3 gamma rays. So a bunch of light in a tightly confined space. This reaction is called an annihilation reaction. It puts out a lot of energy. And so the reason that there weren't any positrons to be seen is that there's a bunch of electrons around. And so anytime there would be a positron, it would meet an electron, and this thing would happen. It would just get converted into energy, and we'd see no more of it. So, fine.
Why doesn't that hold the other way? Why don't all the ones we are made of disappear also?
Yeah, that's a great question, because there seems to be an uneven number of the two, right? And why there's an uneven number of the two is this sort of goes back to the same question that Jacques asked to begin with. Why is it that we're made of matter, right, and not of antimatter? Why is there this imbalance? And nobody quite knows the answer to that question. So we'll get to why we don't know and how we don't know later, but the answer is we don't know. Right? So very shortly after this, actually, it's fine to say I predict this thing that for sure we're not ever going to see, and therefore my prediction is correct even though we're not going to ever see it. That's how string theorists work and so on. But very shortly afterwards, the positron was actually discovered by going up into the upper atmosphere where there's not really a lot of stuff. And so there's not really a lot of electrons for positrons to be hitting right away. It's close to space, there's very little stuff. And so if there was a positron being created up in the upper atmosphere, it wouldn't get destroyed right away. It might exist for a little bit. And so by taking stuff higher up and looking for something that behaves like an electron but bends the opposite way. So because an electron would bend in a magnetic field, if you have got something that's going to bend the other way, but the same amount as you expect for an electron, you know, oh, this is an anti-electron or positron. And Carl Anderson in 1932 first saw this thing. So this thing is a picture of his apparatus with a track for a bending particle that's bending just as an electron would, but in the other direction. And for finding this thing, Carl Anderson became the youngest American ever to win the Nobel Prize at 30. That makes you feel like high achievers. And these positrons are still things that we see today. So for instance, here is positrons, so antimatter, anti-electrons, are things that are useful every day. One way in which they are useful is, well, they whenever they're around, they find an electron, they collide, and that puts out a bunch of light. So that's an easy way to localize something by seeing where the light is coming from. And so one thing that people do in medicine is feed people a bunch of radioactive glucose. And then once the radioactive glucose decays, puts out some positrons. These positrons find electrons, and from the annihilation, you get you get bursts of light. These bursts of light go through the body of the person and are detected. Now, what's the use of that? Well, in a healthy body, most of the glucose is taken in by the brain and the kidneys. In a body with a cancerous growth, a lot of the glucose goes to where the cancer is. And so, actually, cancer detection is done by this process called positron emission tomography, or PET scans, where it's in fact antimatter that's helping detect where it is that the cancer is found. So, yes.
I'm sorry to take everybody's time. You how come radioactive glucose has positrons in the first place? Why isn't it annihilated back there?
Right. So, you're right. Radioactive glucose itself does not have positrons. It's tagged with a radioactive, usually a radioactive fluorine atom, which in turn decays, and part of that decay process, it's got a half-life. So as you eat the radioactive glucose, it still doesn't have any positrons, right? But while it's in your body, it decays, and part of that decay involves a process that puts out both a positron and an electron. So this positron and electron is created as part of the radioactivity from this decay.
What is-
I'm afraid nobody could hear the question, so
Yeah.
if you could please repeat it.
Okay, so the
before
question
you-
is, why is it that radioactive glucose has a positron to begin with? And the answer to it is that it doesn't. It's just in the decay of the radioactive glucose that the positron is created. And we'll talk about how is it that positrons are created to begin with, right? Because we said these things aren't around, so why is it that they're around, right? So it's a good question.
Can I ask you just two
Yeah.
clarifying questions?
Yeah.
You mentioned earlier that out in space the positron might exist for a little bit.
Yeah.
Are we talking nanoseconds, seconds? What are we talking?
No, quite a while actually. So there's occasionally occasionally you might think that we might even get antimatter that's existed for a very long time. It just has to do with how quickly it finds an electron. The ones that are found in cosmic rays are usually created up in the upper atmosphere as well. So then they survive for fractions of a second, but large fractions of a second.
Okay.
Yeah, but that's not to say that there might not be, people are looking for, say, antimatter cosmic rays that have survived for years and years just because they're traveling through empty space and not hitting it.
And just second minor clarifying question. Does this person have prostate cancer based on the coloring? There's a nice, because the heart and the brain I get, and then there's like that.
It might be liver cancer. I think the,
No, but the lower fossa.
oh, that's the bottom. Oh, I see, yeah.
Don't we have any doctors here?
I don't know. Yeah, does anybody want to give a diagnosis? Yeah.
Please respond.
Respond, yeah. And sort of to help answer Zheka's question, part of the reasoning behind saying that part of this decay creates radioactive, from radioactive glucose you get antimatter. We have to explain that this equation goes both ways, right? So even though you can get an electron and a positron to come together and create a bunch of energy, if you have a bunch of energy in a really tight space, as you get from radioactive decay, this equation could go either way, and so you can create, if you have a lot of energy in a really tiny space, create an electron and positron. So the same reaction moving backwards. In physics, at very small scales, the same thing can happen forwards and backwards, and there's no, those two things are symmetric. It's only at larger scales that things move. You can tell a video moving forward in life versus backward in life if you were to have a video camera that was small enough to look at atomic scales. You wouldn't be able to tell. Same thing, forwards and backwards. And so this process, the reverse process of annihilation, is called pair production because you can only make two things at a time, a positron and an electron. So you can't just make one because of a law of conservation. You can't make a positive thing without a negative thing. So now we're going to get to Rebecca's question about why is it that we've got matter and not antimatter, by talking about what happened, we think, very close to the beginning of the universe. So here is a picture of life shortly after the Big Bang. Just right after the Big Bang, we think there wasn't matter or antimatter around. There was just a really large amount of energy held in a really tiny space. And once you have a really large amount of energy held in a very tiny space, of course, you can have this reaction, right, where matter and antimatter is created by the reverse of the annihilation reaction, by the pair production reaction. You can make positrons and electrons, or quarks and antiquarks, or protons and antiprotons, from having a bunch of energy in very tightly confined. And luckily, at the Big Bang, that's exactly what we had. I don't know, luckily or not luckily. But of course, you for every one you make of the electrons, you make one positron. Right? You make one proton, you make one antiproton. You make one quark, one antiquark. And then as the universe continues to expand, there's not that much tight energy, in a small space, so you can't keep doing this, but you can, those things can still collide and annihilate. So you can still have the reaction where an electron and a positron come together and just make a bunch of light.
So basically it means that it's just the antimatter that we encounter in the wild. It's those lonely antimatter particles that just didn't make the couple yet.
Well,
From the
maybe,
beginning.
but the thing is, at the beginning, the universe was a lot more dense. So actually, pretty much everything should have met something by now. But you're right.
It's
that
pretty
makes,
much the same things, because if it got converted into energy at some point and then like got separated again, we're just trying to, like, if the law of conservation is still valid on that scale, it just means that there has to be a balance. There has to be an equal amount of
Right.
antimatter and antimatter, right?
There has to be an equal amount of matter and antimatter. You're completely right. And by that logic, there either has to be the same amount of antimatter somewhere else as there is of matter around here, right? Or, nothing has to exist because everything has to have met a pair. And based on the, lonely individual antimatter things that we notice, we know that it's not the case that it's likely that there's a bunch of antimatter somewhere else. And so the only solution is that everything got destroyed and there's nothing left, because everything must have found a pair, except the little tiny amount of antimatter that we've still got, and all the matter that we've still got. Yeah.
Does it mean that the scientists are searching for some potential fuel?
For some potential fuel.
Because
Well,
every
you can-
reaction is actually a fuel.
Which?
Well, I mean, the matter and antimatter collision.
So when
means-
you have a matter-antimatter collision,
Yeah.
it makes a bunch of energy, right?
Yeah.
As
And then
you're
energy
aware.
means fuel.
And that energy can be used as fuel for something else,
Okay.
right?
And
So if
it
you
is oil, so yeah.
so if you found this spot where everything is made out of antimatter, you become really happy. You grab it and destroy it all and create a giant amount of energy and use it as fuel. And I think in Star Trek, this thing is used to fuel the warp drive of your spaceships. In Angels and Demons, this energy is used to blow up the Vatican. So you can use it for various uses, positive and negative.
But you mentioned that it
Yeah.
went different direction, right? So if
Yeah.
you, on this picture it goes right, then all the antimatter is supposed to go left.
Well, this is the difficulty that arises when you try to picture a three-dimensional thing,
It's just the
1.5 dimensional.
No, but why not? I had exactly the same thought that maybe there is like the universe is growing in two directions, right? So,
Yeah.
and there is like antimatter, just like the bunch of antimatter ended up on one
Anti-universe.
side,
It's
and
just
Yeah.
another universe.
So there's actually a reason why we think that's not the case. Can anybody
because it
guess?
collide at some like there is a point where it started, so it should start colliding.
Right.
Right
So
there,
if it started expanding in two ways, there's going to be a boundary, right,
Yes.
between the two. And at that boundary,
so big that it
what's going to happen? There's going to have
really fast in another direction.
But what about theory of parallel universes?
Well, what about the theory of parallel universes? Maybe in some parallel universe, there's these people talking about this with made out of antimatter, and they don't know. They think they're made of matter, and they're calling it. So, the thing that I want to point out is that we can actually tell of the amount of matter and antimatter that was made, what part survived and what part got destroyed in this annihilation. And it's basically everything got destroyed, except about one part in 10 billion or so. So everything, all the matter that you see in the universe all around you is about 1/10 billionth of what there was. And everything else met its antimatter pair and is no longer with us.
And this is what is pushing the universe apart, basically? That's
No.
what's fueling the expansion, or?
No, this is a separate thing.
Okay.
Can I ask you,
yeah.
so basically this 10 billions is probably a miscalculation on the God.
Yes.
Because it was annihilated at the same rate, right?
Right. So you would think 1 in 10 billion is kind of a small error. You don't even have to worry about it, right? just like round off. But then, as you can see, the effects are pretty significant. So check your calculations. So yeah, I mean the question is why is it that even though we said that for every one there must be one, it's actually for every one there's one and 1 in 10 billion, right? Why is it like that? And there's several potential answers to this question. One of them being that, like Yosha suggested, there's antimatter going the other way. Somewhere else in the universe, there's a galaxy made out of antimatter that was just expanding in the other direction. Or maybe at the beginning, right at the Big Bang, it wasn't just a sea of energy that got converted into matter and antimatter. There was something there to begin with. This is a thing that we can't really test very easily, so we're just going to ignore that possibility.
Is it theoretically possible for that matter to have existed within that dense sphere of energy, though?
If there was no way to convert it into something else, right?
It would have
Because
just been compressed, but
right,
not destroyed.
if there's no, so it just seems extremely unlikely. But I don't think we understand sort of that situation well enough to answer your question. Maybe the conservation laws that we said where this reaction can only make one piece of matter and one piece of antimatter were different in the early universe, because the early universe was at a very high temperature and a very high energy density, so maybe the laws were somewhat different, and we'll only find out how they work by getting to that really high energy situation. Or maybe there, at the beginning, an equal amount was created, but something about matter and antimatter is slightly different, so that sort of over the evolution of the universe, it came to be that matter is around and antimatter is. Yeah.
We see light from other stars. How do we know what are they made of? Maybe they are made from antimatter.
Right. That's you were thinking back to this ham sandwich, anti-ham sandwich thing. We don't know from light whether the light comes from matter or antimatter, because light is not matter or antimatter, right? And so, if you look at light, you have no idea. It could be that this light is made out of antimatter.
So there is no anti-photons?
There's no photons. I mean, you can think of photons as their own antiparticles, maybe. Yeah. Yeah. Photon, and I mean, if we define this thing as a reversal of charge, and also parity and time, then a photon is going to be its own antiparticle in a sense, right? So there are no antiphotons. We can't tell from light whether it comes from an atom or an anti-atom or anything like that.
It's a very gay particle.
Well, how do you, I mean, it's more of a hermaphroditic, I guess, is the correct, yeah.
What about neutron? The neutral in charge. What is this anti-neutron?
Right, so neutrons are neutral in charge, but inside them are quarks, right? And quarks have charge, so you can make an anti-neutron and it will be neutral, but it will be made out of charged anti-quarks. So instead of ups and downs, it would have anti-ups and anti-downs.
Do those annihilate the same way? Like two neutron and anti-neutron?
Yes. Yeah, these are not things that are easy to make or study, so we don't really know that much about them.
What if we take electron and anti-neutron? Would they annihilate?
No, they wouldn't, because an electron and an anti-neutron, there are certain laws of conservation, right? Like an electron and a proton, for instance, one is negatively charged, one is positively charged. But if you put them together, they don't annihilate because you can't convert proton into.
They would interact, right?
They would interact. So yeah, a neutron, an anti-neutron, or an anti-neutron and an anti-electron, a positron, would interact, but you wouldn't get an annihilation because there isn't. You can't conserve lepton number or baryon number. Basically, the number of electron-like particles and the number of heavy particles that contain quarks.
So can you create atom of having like anti-neutron and then electron?
Of course.
You could?
Yeah.
Okay.
Yeah. Or you could, and we try, and we do. No. So I shouldn't say of course.
What kind of properties they have?
Yeah, we'll talk about it. But the question is, would they have any properties that are different from a normal atom, right? And that's kind
Can
of.
you make a sandwich out of it?
Can you make a sandwich out of it, right? Yeah, not yet, but working on it. Feeling pretty hungry, so. All food today guaranteed made of matter, not going to annihilate.
Even beyond meat?
Good diet.
No. Very, very highly energetic, lots of calories. So, I don't know if you heard, I think about last month there was the first all-female spacewalk actually at the International Space Station. And what these astronauts were doing were fixing an instrument called the AMS. And the AMS is an instrument that looks at cosmic rays, looking for, in the same way that Carl Anderson looked for a positron and found it, they are looking for signals that would tell us about this boundary between matter and antimatter, this boundary between the world as we know and the anti-world, which should involve a lot of annihilation. So you'd expect this three-dimensional, basically burning wall. And since we haven't ever seen one, we don't know exactly what it should look like. But we have an idea for what theoretically it should look like, and we know that we don't see it.
But why there should be a wall if it's empty space between us and that star?
Well,
Why can't that star
because
be
empty
generated?
space is not that empty, right?
I don't know if they survive.
Empty space is pretty full. It's got, you know, a density of maybe a few atoms per square meter at the very, very emptiest, right? So you are extremely unlikely to survive. The reason that we still see some is because, you know, there's a lot of them being generated. But the vast majority, if you make a bunch of antimatter, you know, antimatter is being made all the time, and you fling it out into space, 99.999% of it will hit something pretty soon. Because also, it'll be attracted, right? You have a negatively charged thing and a positively charged thing floating, they'll be attracted. And so things that are, the universe is mostly a lot of plasma, right?
Is
A
it
lot
the
of
same
ions.
kind of charge?
What's that?
The same
Yeah,
kind of charge.
it's
that will
the
be
same
attracted?
kind of.
Yeah, it's the same kind of charge. A positron is just a plus charge, like a proton, right? So if you have a cloud of, you know, protons and anti-electrons,
But
yeah,
neutrons and neutrons will not be attracted.
that's
neutrons
right.
and
They will not be attracted. Yeah.
With a sufficient volume of space,
Yeah.
would there not be a transitional zone? And what, has anyone calculated what that volume would be for it not to have that explosive kind of boundary?
Right. So, I guess the question is, could we be expanding fast enough, and these things getting farther away from each other fast enough, that even though they're flying in all sorts of ways, we would never actually get an interaction zone. And people think that we should have one, given the expansion rate of the universe and given how much stuff there is even in its emptiest corners. But it's a possible answer, right? It's possible that somewhere far away that we're not seeing, there's a bunch of antimatter. As far as we can tell, we should get this burning wall, but maybe we just don't understand what it should look like. Yeah.
Everything you talk about today it's confirmed theory. Confirmed. It's known community, right? That's true.
I will try to say true things. I will try to not
I mean,
say
it's not
false.
it's not extreme theory.
Or
right?
it's just a
accept-
desire for symmetry.
Yeah, I mean, I will. It's everything. I'm an experimental scientist, so everything I want to say is something that is being looked at via experiment, right? At least, and so it's a thing that it's either a hypothesis that's being tested, in which I will say it's a hypothesis that's being tested, or it's a thing that we know. Yeah.
This instrument, like EMS, is it they looking at some specific direction, or how they like navigating through the space?
So I don't really know, but I think the idea is that there's sort of directions where you're more likely to see things coming from outside the galaxy, right? We're in a galaxy which sort of looks pancake-ish. And so if you point it away from, in the plane of this galaxy, you're more likely to see things coming from outside the galaxy. And I think that's generally the way that things that are looking for extragalactic signals work, but I don't actually know about the AMS specifically. If somebody else in the audience knows, then please feel free to interrupt me with answers as well as questions. Yeah.
Let's move to the next slide.
So the question then, could it be that there's something different about antimatter in the way that it behaves? And what?
Can you move back?
Yeah.
Well, a few words about the dark matter.
Nobody really knows anything about dark matter, or that much. It's unlike antimatter, which is, I can show you what it is, and can make it and study it. Dark matter, we can only tell basically from its gravity behavior that it exists. We don't know what it is.
Are we sure that it exists?
We're pretty sure that it exists because the other possibility is that gravity acts differently at when you're really far away from something, right? So the reason that people think dark matter exists is because galaxies, the way that galaxies spin, Vera Rubin was the person that sort of took this information. You can tell from how galaxies spin how much stuff there is, right? You can, just by sort of figuring out how easy it is to spin something up, you can tell how heavy it is, right? So if you can look at how fast galaxies are spinning, you can figure out how much stuff there is, and then you can look at the galaxy and figure out, how many stars there are in it. So you can get an idea of how much stuff there should be versus is, and the discrepancy is the dark matter. But the way that you might think, well, what if gravity acts totally differently at large scale, so this stuff isn't really attracted and isn't really spinning around like you think it should be? And the reason that we think that that's not the case is because we've actually seen a collision between two different galaxies. And when you look at a collision between two different galaxies, you notice that there's now the center of where all the stuff is going to be different than the center of where all the light is, right? In a galaxy that's spinning around, you can say, okay, at large scales, the stuff isn't spinning around like you're expecting it to, but it's still centered around the center of the galaxy. If you've got galaxies colliding, the center of the two things is shifted. I don't know if I'm doing a good job of explaining this, but this is a sign that it's not just that we don't understand how things work at very large scales, that there's actually something there. So I don't know if we can say we know that it's there, but we're more than just guessing based on rotation.
Is it possible that the fact that we cannot see lots of antimatter somehow relates to
dark matter?
Yeah, so maybe it's
possible.
just trapped in there for whatever reason.
For example, right, it's possible that dark matter and antimatter react somehow differently than matter and antimatter.
It's just basically
Yeah.
just that, right?
It's very possible, and because it is, what we want to do is, dark matter, as far as we can tell, is sort of all around us. So if we make a bunch of antimatter and observe it closely, we can see maybe it's interacting with dark matter in a way that we wouldn't expect. And if we did that, basically it would, as I said, as far as I know, an anti-sandwich is like a sandwich, right? So if I make an anti-sandwich and look at it for a really long time, and notice that something weird is happening to it, that tells it apart from a regular sandwich, might be dark matter that it's
The
interacting.
question is like, if we can see it and we know that it survives in an empty space, can we just gather a lot of the antimatter in one space and try to
Yeah.
something out
Yeah,
of it?
yeah, that's what we try to do. That's what we try to do at CERN. We try to make a bunch of antimatter, put it in a big vacuum so that it's not surrounded by a bunch of matter that it would then annihilate with. Keep it there for a long time, and see, is it acting similarly to exactly the same to what we expect, or very slightly different? Yes.
Do we know anything about anti-dark matter?
Technically, it's dark antimatter.
So, I mean, this is a hard question. We know sort of as little as we know about dark matter multiplied by the difference that we know, like how much less we know about antimatter than. So it's possible that this is a thing that antimatter also has dark matter also has an antimatter analog, but it's also possible that it doesn't. Yeah.
I have a question on the previous topic about finding it. Couldn't it all be just an antimatter?
Well, if it is, there needs to be a reason why.
Sorry,
all
do you mind repeating the question?
Yeah, the question is, couldn't the antimatter all be in black holes? And it could, but there needs to be a reason why preferentially antimatter went into the black hole and not matter, right? It can't just be, it can't just be, we can store it there. Like if we had a bunch of antimatter and we really needed to get rid of it, we could go and put it in a black hole.
Wouldn't it annihilate?
But it couldn't, yeah, I don't know how antimatter in a black hole would, you could have a black hole, I suppose, that was made entirely of antimatter, but there has to be a reason for that to have, for it to have started and not a matter one. So.
Don't we kind of know how black holes were created, how they evolve? Because if we do,
yeah.
then probably antimatter couldn't appear there.
Well, I mean, you could have had stars made of antimatter, and those stars have gone supernova, and those supernovas created an antimatter black hole. But it's, like I said, there needs to have been, for that process to occur, there needs to have been a bunch of antimatter hanging around to begin with. So I think a more likely thing is that there's some difference, or there is some violation of conservation rules at the start of the universe, which is probably the most likely. I guess just very quickly, because for time reasons, I will say that we want to figure out whether there's any particular difference, and the way to do this is to make a bunch of antimatter and put it away from matter in a bottle, right? And this is a schematic of CERN, which is where the Large Hadron Collider is located. The Large Hadron Collider is the big ring at the top, the LHC, where people speed up particles to extremely high speeds and then collide them with each other, which makes really high energy in really tiny space, right? That's how we got the positrons, antipositrons to begin with, positrons, electrons to begin with. That's how you make interesting particles. You just put a bunch of energy in a really tight spot and then hope fun stuff comes out. And that's what a lot of physicists devote their lives to. But over here in the corner, a tiny portion of those particles that were going to be collided at extremely high speeds are deflected over to this light blue area where they hit a foil, and at those energies, you don't get fun particles, but you get to make protons and antiprotons, which then, because one is positive, one is negative, you get to catch the antiprotons, and then they're sent to the light blue area called the AD, which is short for antiproton decelerator, which is an accelerator run in reverse. So you slow down the antiprotons, and you try to catch them, trap them, and look at them to see if there's any difference between them and their matter equivalent. And this happens in this building called the Antimatter Factory. This is a photo by my friend Joe.
Where are the pipes?
Underground. Well, there's so much antimatter, so little antimatter that the exhaust, we're a very green and environmentally friendly factory. All of the exhaust is kept underground. It's buried. So there's 6 experiments working there. Alpha, ATRAP, AGIS, Asakusa, BASE, and G-bar. And all of them, the large presence of A's is because fun acronyms having anti-proton or anti-hydrogen or anti-matter in some way. All work on catching this stuff and looking at it. So, as I said earlier, the easiest atom of matter is hydrogen. The easiest anti-atom of matter, antimatter, would be an antihydrogen made of an antiproton and a positron. And this thing, if you had it, would allow you to do some interesting experiments on whether antimatter is similar to matter, because first of all, it's neutral, so you could try to drop it and see if it works with gravity the same way. Second of all, you can have the same kind of energy transitions as you have in an atom, right? Like the same thing as neon lights are a specific color because there's a specific energy for a neon electrons in a neon gas. You could have specific energies for electrons in a hydrogen gas. Those are part of the lights that you see in the northern lights and the aurora borealis. If you had the same colors in anti-atoms, that would show that the sort of energy behavior of the two was the same. So, and we can measure frequencies very, very precisely, colors very, very precisely. So that's one way to get a very precise measurement of whether antimatter and matter is the same. So we do that. We try to trap them in this thing. The language in this is Welsh. Sorry about that. But if you're looking to learn some Welsh, here.
English is not
We'll add a third option to the vote for which language to have these discussions in the future. But this is a group I used to work with, and they're led out of Swansea University in Wales. So all of our materials are also available in Welsh. Here's the English version. It's okay. But you have this trap, which, because antiprotons and positrons are electrically charged, you can arrange electric fields so as to put them all in a small, tight space, and then collide them together and hope that you make some antihydrogen as a result. And this is what it looks like in what's going on? Respond to me, please. Doesn't want to show the next picture. There it is. This is our experiment in real life. there's about a 3-meter long superconducting magnet that you have to fill with helium every other day. And there's our boss, Jeff, who you also saw at the beginning hanging out with Metallica. He doesn't just hang out with Metallica. He has other duties. He, for instance, drilled the concrete holes where all of these things are placed. Or he started drilling these concrete holes, and then he got called away. And so he came to me and said, you know, drilling concrete holes in concrete is a useful life skill. Some of these holes are drilled by me. In the end, when you make antihydrogen, you can no longer trap it with an electric field because it's no longer positively or negatively charged. You want that because you want to test antihydrogen because it's got the energy and the gravity behavior that you're interested in. But it also means it's very hard to keep. And so we have these extremely strong magnets that we use to keep it because it's still magnetically sensitive, even though it's not going to be trapped by electric fields. But even then, you know, we get maybe from the antiproton decelerator, we get enough antiprotons to make tens of thousands of trap tens of thousands of antiprotons every 2 minutes, make tens of thousands of antihydrogens every 2 minutes, and we get maybe 20 of them every 2 minutes in our 3-meter long bottle. So that's very, very few, but it's the best that anyone can do with keeping antimatter.
For how long can you preserve it? Like, for how long can you do experiments?
Yeah, so for instance, there's this group called BASE, our friends down the hall. This is their boss filling the liquid hydrogen in their experiment. I'm not sure he actually does that. But they are able to keep their antiprotons for months. Their vacuum is that good. So they're the ones that are looking for interaction with dark matter, so they keep it there in that vacuum for months. And seeing how it rotates around their trap, the thing is trapped in an electric trap, so it's traveling around, and see if there's anything different about how it's traveling around, tiny differences over the course of months. We generally can keep ours for about a day, if we want to. We sort of get bored after that. It's very, it's not a fun job to.
What does it mean, them, us?
Yeah, sorry. Different experiments working with antimatter. Once this antiprotons are created, there are, as I said, 6 different experiments that are working on it. I shouldn't say we or them. Basically, different experiments looking for any difference in behavior between antiprotons and protons, antihydrogens and hydrogens, whether they interact with dark matter, whether it's if they have a slightly different light spectrum than we think, whether they fall. You know, we know that normally matter falls, everything we know on the surface of Earth falls with 9.81 meters per second squared, right? Downward. But we actually don't know whether that's how antimatter behaves at all, because all the antimatter that we've made is generally electrically charged. It's plus or minus, and so it's being attracted much more strongly by electric fields, and we can't really see whether it would fall down if we just let it go.
But you said you're able to make some atoms.
Yes, we're able to make some atoms, and then but at the temperature that we make them at, they're, you know, hustling around inside the trap, if you let them go, you sort of get a picture of how fast they were moving around. You have to get them very, very cold before they're slow enough that they just fall down. And
Can you get them that cold?
so, I mean, people are working on this. People are working on either doing that or getting basically enough of them that even though they go in all directions, on average, there's a small difference between how many go up and how many go down. And that's sort of the place where I have to tell you stay tuned, because we don't have an answer for you.
Alex,
Yeah.
One thing I don't understand, if you hold them for a day or longer,
Yeah.
What do you measure? How nothing happens to them, right?
So
Doesn't say Planck's constant, limits you in your measurements?
So, I mean, those are two different questions. What are you measuring if you just hold them? If you just hold them, you're right, you're not measuring anything.
Then what was the point of
But-
holding them?
So, yeah, so you can, if it's a charged thing, you can make it rotate inside the trap and measure the frequency of how quickly it rotates. If it's a neutral thing, you can hit it. So the way, for instance, if we're looking at for the energy spectrum, as I was talking about earlier, whether it's got the same color. So if it's got the same color as hydrogen would, you would hit it with light of that color and it would react, right? So you hold them there and you hit them with light with that color and you see if there's a reaction, right? You need to hold them there for a while because, you only got 20 atoms or something and you're hitting them with light. It's not always going to interact. So it's good to be able to hold them for a long time. But you're right, Eugene, you're seeing the reaction from what happens when when they're no longer being held. And you try different things to not have them be held anymore. And same with gravity, you hold them for a while until they're cold, then you let them go and you see, how do you see that whether they fell up or down? Because they hit the wall, and at the wall they find an anti-version of themselves and annihilate, right? So you only really see them when they're gone.
Then the second question doesn't matter, I guess.
Did you have any experience, or did you make any experiments in terms of dependency on the number of antimatter particles versus temperatures?
So the question is, what's the dependence of the amount of antimatter particles on the temperature? And the answer to that is the lower, so we're limited by the traps that work on antimatter are limited by how hot something in them can be in order to still keep it. Because if an atom or an antimatter atom is moving very fast, it can overcome the electric or magnetic field trap that it's inside. So whoever is working on gathering these things has to ensure that the temperature of the whatever antimatter is low enough that it fits inside, and basically all the experiments are limited by that, are limited by making a bunch of antimatter that's hot and then losing all of it.
So what does it mean hot? Is there very few of them, so it's pretty much a vacuum of antimatters. Like, what does it mean hot?
Yeah, sorry, fast.
Fast, okay.
Yeah.
I actually had the same question and I wanted you to, and guess the answer, but I wanted you to clarify. You can say hot or cold, say this is just flying somewhere quickly,
It's a speed.
Yeah.
or you can say in terms of entropy, that we don't know much about it.
Yeah, so
and
they're,
therefore it's.
yeah,
So you mean the first?
yes, yeah. They're not thermalized because there's so few of them that they don't collide. They don't really have a temperature, but they have an energy, each individual
When you say we have to make them cold, means we have to stop them. And then
Yes.
we can drop them.
yes, exactly. Yeah.
Did I understand right that you're looking for differences because those differences will explain why there is unequal numbers, right?
Right, yeah, we're looking for any differences. I don't know if those differences will explain anything, but right now we have nothing to go on.
So it seems like we are at the stage of a child who is trying to get down the slide, and interesting thing happens when you go fast.
Yes,
Okay.
have to figure out why. So I think that's it for me, actually, unless there's more questions. Yes, with that.
Yeah, you're talking about these two different facilities there,
Yeah.
like some, it's whatever, antimatter factory.
Yes.
And the other one, here you capturing the antimatter, but the instruments is the same. When you saying we're looking at it, you mean is it the same instruments differently tuned, or is it different instruments?
So you mean with matter?
With matter and antimatter.
With
yeah.
well, ideally you'd have the same instrument in the exact same way, right? But it's kind of difficult to create because there's so much specific things that you have to do in order to be able to make and keep antimatter, right? You have to start with antiprotons that are made in this specific collision. You have to start with positrons that are from a radioactive decay. You have to have this giant superconducting magnet with a super high vacuum. If you want to try the same thing with antihydrogen, you just like go buy a gas bottle of hydrogen and plug it in and shoot some light at it. So it's very hard to say, okay, we need to make this extremely complicated, many $million thing to recreate the conditions of the antimatter exactly. So it is in a different environment. But everything here, every experiment that's done on antihydrogen is done in that facility in the antimatter factory itself.
Yeah, but the instrument is looking the same, like you searching for some spectrum of the light coming from it.
Right, and this instrument could be used for looking for that light with hydrogen. Yeah.
So where does the misconception, I remember like when the first news arrived that CERN is building the Large Hadron Collider,
Yeah.
and people were panicking because they were saying you're basically creating mini black holes, like micro black holes, nano black holes. I'm not sure what the scale is, but
Yeah.
how does it not blow up? Going back
Yeah,
to
so those, like I said, when you collide these things, you make a giant amount of energy in a very tiny space, right? And since that energy is equivalent to matter, I think what happens is you have a very tiny, very dense object. And I'm not sure I'm qualified to answer this question. Maybe somebody else can take over from me. But the idea is that if you have that much energy at such small length scales, basically you get a collapse because everything is just too high an energy density at too small a scale. And you're trying to create as much energy density at small a scale as possible. But I think the misconception comes not from the idea that you might be creating miniature black holes, but from the idea that these tiny black holes are then going to grow into larger and larger black holes and slowly eat the world. That's the misconception, because if you have a really tiny black hole, it's going to evaporate very quickly, and it doesn't live for very long. What's that? Who supports it financially? It depends. The European Organization for Nuclear Research has member states, which are most states in Europe, as well as some states outside of Europe, and part of their scientific budgets, so taxpayers generally.
I have the same question, but in a tougher form.
But not Canadian taxpayers.
ROI, return on investment. So when you are writing grant proposals,
right,
you are saying this is going to be good for humanity in some way.
Yeah.
What are you writing there? What do you write there?
I mean, a lot of it goes back to sort of trying to justify basic research, right? You look at things that antimatter research has led to, and it has led to, for instance, things like CCDs, I believe, right? It doesn't have anything to do with antimatter itself, but it came from trying to find a better particle detector for, I believe, for antimatter research.
What's CCD?
The charge couple display, the thing inside your digital camera that allows you to take digital photos.
Sensor.
The sensor, basically, for a digital camera. So a lot of the stuff that we, to study this thing, we have to push engineering capabilities to the limit of how sensitive instruments can be, and making more sensitive instruments is a thing that's worthwhile for the world. You know, a lot of antimatter stuff is because there's this sort of sci-fi idea of rockets powered by antimatter and all of this. There's thought that this is potentially interesting research from either an energy perspective or a military perspective or things like this. Basically, we say it's basic science. A lot of the time, you find cool stuff. In the end, this is a lot of money, but compared to how much money it takes to power the LHC, it's very, very little. And so we basically are lucky in just sort of getting the scraps off of that. They're doing this stuff anyway. So a lot of our requests for money are.
So, how difficult is it to get a job at the place?
How difficult is it to get it? I don't know.
Like what type of job?
I think.
Physicist? Scientist?
I think it very much depends on what kind of job you're looking for. There's thousands of people working there and tens of thousands of people affiliated. So it's definitely possible. It depends on what you're interested in. They take there's a job site at home.cern.
Just take motivate our kids to go to physics and continue research.
I mean, if my personal experience is that it's an experience. It's type 2 fun. It's better looked at from the. It's fun in retrospect, not necessarily that much fun at the time.
So another question. So the God particle or
the Higgs boson,
right? Like where does it come? Like how does it relate to the rest of it?
Well, I mean, the Higgs boson is a particle that's made. The reason that it took so long to find is that it's quite heavy, and if you have this E equals mc squared equation, that means you have to have a very large amount of energy in a very tight space in order to be able to make it. And so the reason that it took so long to find is that you basically need to speed up whatever you're going to collide to high enough speeds that a collision is going to make enough energy in a tight enough space to make a Higgs boson. And once you've got that, you're going to make them every once in a while, but most of the time you're just going to make, you know, electron and positron, or a proton and antiproton. So it's one of those situations where even if you have enough energy to make something that's heavy, it's just, as far as we know, just a matter of luck what gets created.
But where is it sits in terms of like antimatter, matter, like where
It's so Higgs boson is, as far as I know, its own antiparticle as well, like a photon. If somebody wants to correct me on that, then, but I believe as a so it's a boson, so it's not made of quarks, right? It's not made of leptons. It's right. So it's not really matter. So it wouldn't.
but
So
it have a weight, right?
it has a
Mass.
a weight, right? It does have a mass.
But nothing else.
Speed.
So it's, yeah, so, I mean, it also, like a bare Higgs boson sitting by itself also doesn't live for very long, so you can't find out its properties super well. Right now we know its mass, right? I think that's, and things that it can decay to. So, I mean, it's part of what we expect in terms of what would make the creation of other particles make sense. And the Higgs boson, if there are other Higgs boson-like particles with much heavier masses, it might actually help explain this anomaly between matter and antimatter in some respect, because there is basically in the intermediate process of creation of particles and antiparticles, there is that can be mediated by different bosons, and if there's a bunch more bosons than we don't know about, then maybe there's more stuff there to find out. I don't know if that's a helpful answer, but the answer is yeah. Yeah.
When you smash things together, do you know that you're going to get electron and positron, or proton and antiproton, or is it just?
So you
random?
don't. It's a matter of luck, but it's also a matter of how much energy you're smashing them together, right? You need to have enough energy by E equals mc squared to make the masses that you're looking for. So you can be sure that you don't make a proton and antiproton by having enough energy to make a positron and an electron, but not more than that.
And if you do them separately, how do you then construct an atom out of these things flying around?
Yeah, so that's complicated, right? You have to slow them down, each individual one, and then you have to bring them together, and they have to both be in electrical traps, and then you have to bring those traps closer together, and then hope that they collide, and they're going to be attracted to each other because they possibly. Yeah.
Yes, sorry for jumping in. Let me propose that those people who are hungry just
Yeah,
go in it, and those people who are hungry for
I want to say
information.
thanks. Come and talk to me around hours.